Well, good morning, good afternoon, good evening, wherever you are around the world. This is Photonics for Quantum 2. My name is Don Feiger, and I'm your host. This is our last week. It's been a pleasure to deliver all of this content to you over the past, 6 weeks or so. We've just had a fantastic series of talks, and this week is no exception. We don't have a talk every day this week, so I wanted to give you that programming note. We won't have a talk tomorrow. We will have a talk Wednesday and another Thursday. And then that'll be it. As far as we know now, Thursday will be the last talk. As usual, I'll remind you that you can view and listen to all these talks in their recorded versions by going to the RAT PFQ2 webpage. So before passing it over to today's speaker, I'll once again thank our generous sponsors who've been very supportive and have given some sponsored talks. Their logos surround me. You can see them there. I would also encourage you to go look at the sponsor exhibition, which of course is virtual. So you could find that by going to the PFQ2 webpage and clicking on a link near the top, and then that'll take you to another page, which is essentially a virtual exhibition. So with no further ado, I'll hand it over to today's speaker, Christine Silberhorn, who's from University of Paderborn, and she'll go ahead and give her talk now. So Christine, when I hand it over to you, if you could go ahead and turn your video on, and I'll turn mine off. We can see you just fine, and if you could bring up your slide. We can see it.
Fantastic. Let me try to just go into the presentation mode.
Mm-hmm. That's perfect.
Okay. Well, thank you very much for the introduction, and actually, thank you very much for giving me the opportunity to present my work in this framework in these very unusual times. I think this is true for all of us. It's a great honor to be part of this thing, and I'm happy to present our work on nonlinear integrated quantum optics. What you see on this slide already is one of our devices. It's actually, as you will learn later on, a quantum pulse gate device where we have waveguides and we illuminate that with green light. As already said, I'm presenting the work which is done at Paderborn University. And I would like to take the chance to briefly introduce also my group. So I'm heading the Integrated Quantum Optics group. And in fact, this group has several subgroups. And the reason is because we think that if you really want to do integrate quantum photonics, that you need a lot of different expertise. I'm very happy that we have all of these different expertise in one group, which is at Paderborn University. So let me briefly start. What is this different expertise I'm talking about? I'm talking about nonlinear integrated devices. And for them, you don't have fabs as you have for passive devices, as you might know. So what that means is that you also have to develop technology. The technology which we use is based on technology which is well established in photonics, but we do it for quantum applications. And what we basically do is we produce nonlinear integrated waveguide devices, mostly based on lithium niobate, some of them KTP. And the person who is heading that or who is responsible for that is my group leader, Christoph Eigner. Now, this is part of the story and is probably the most traditional one. What we do then is, based on that technology, we build out these devices. What I mean by devices is not just photonic devices, but quantum devices. So we design them, but we also need all the integrated optics know-how, such that we build up optical circuits, we do the modeling, and the modeling is very important because it's a feedback to the technology. So we basically, based on our technology, we design and fabricate customized devices. Last but not least, we also need the quantum side. And the quantum side, so to speak, if you want to have quantum applications, we should really come to the point where we can do complicated networks. What I mean by that is networks, of course, you might think of quantum communications, but also quantum simulations, quantum sensing. And this group, which is headed by Benjamin Brecht, the networks, we basically take the ideas from the quantum community, which where I also originally originated from, and this gives us really the design rules. Altogether, all these different parts have to play together to really get a high performance quantum system. And I have to say that I really enjoy to work with all these different people together. Now, let me give you the outline of the talk. So I was thinking, what could I present to this kind of community, which has a lot of photonics know-how, but also quantum know-how. And I tried to find a compromise. And I want to talk about two topics in my group. The one is integrated quantum optics. And this is heavily motivated by the technology side, as well as the devices side. And you will see, what do we really design? What kind of structures are we interested in? What do we have to care about? And I should say, this part is heavily based on know-how, which the photonics people have a lot. And the second part, I would like to go from the opposite. This is heavily motivated by quantum optics, by fundamental research. And I want to show you there, if you have these special devices, if you have new concepts, how do we really implement them? And what is driving the field there? Altogether, all these two things come together because you need them. But I thought it's a good way to flash you through these two quite distinct topics, but I hope you will see how they come together. So let me get started with integrated quantum optics. And I'm sure that you have heard a lot about integrated quantum optics. And I was thinking, should I introduce integrated photonics in general? But I want to say that I concentrate on the nonlinear part. Not that the other things are not interesting. By far, I think it's great that there's a completely new community has formed, but I wanted to focus on the research where we are really strong and what we want to do. So let me start with a vision. I told you already that we work with lithium niobate, and we are working with the lithium niobate platform. So what does that mean? So what we want to have is ideally one monolithic chip. And on this chip, we want to have different sections with different functionalities. So for example, we want to have on one waveguide periodic poling, and this is useful to produce photon pairs, so the quantum state generation. Then we have here, you see these intersections, which are directional couplers. So you want to be able to have routing, which you also have in passive system. We have the great advantage with lithium niobate that we can have fast electro-optic control. And this is, of course, well known. This is why lithium niobate is really strong in industry, where you drive all these modulators. And of course, here we want to use also this beneficial feature that we can electro-optically drive systems. And for that, we can have polarization controls or polarization converters. We can have phase shifters. And this is another important ingredient. And then we can also have simple photon conversion. For example, if you want to interface system and want to convert wavelengths. Last, I just want to mention that we also can integrate superconducting detectors, and there's a junior professor at my university who is really focusing on that. So what is it what we want to have for quantum optics system there? Well, we want to have minimized decoherence, which means we have to have really low loss waveguides, and this is why it's beneficial to base your system on a well-established technology. And this is why we started that. And you will find the technology we're using is really extremely well-established, although we're developing new things now too. We have the stability and the scalability. Well, you get that for all integrated photonics. And the benefits of a nonlinear material is that you can have highly efficient photon pair generation because you have a Chi2 linearity and fast photon routing. With fast electro-optic switches, and I think this is also a very strong point, which is really a great advantage of this platform. The vision we have, we want to implement complex quantum circuits on this platform, and we want to develop all tools which are needed for that. Now, let me go a little bit more into detail. I'm sure that you have heard of parametric down conversion. This is the workhorse of many systems still, how to produce quantum light. Now, how do we do that? We have in our system always a waveguide structure, which is consisted of a nonlinear material, and we pump that with a strong laser pulse. By pumping it, we have a nonlinear action between the crystal and the light, and this creates a signal and idler photon pair due to spontaneous decay. For this process to happen, energy momentum conservation have to be obeyed, where you find these conditions here, and this here on the right-hand side is nothing else like phase matching, and we have quasi-phase matching. This is where we need the periodic polling. Now, doing these things in waveguides gives you the advantage that you have a strong confinement of all optical waves, and you can have very high efficiencies. And the interaction length can be up to 90 millimeters, so it's really quite long. And I will come back to that in a minute, what that means. Now, what technology? Let me briefly flash the technology we use. The waveguide, to be more specific, we use our titanium in-diffuse waveguides, where we pattern with photolithographic methods a titanium stripe, which we then in-diffuse, and which gives us the waveguide. Now, the advantage of this way of the titanium in-diffused waveguides is that we have TE and TM guiding. We have a high nonlinear conversion efficiency and also relatively high coupling efficiencies to fibers. I will come back to that, where we also work there because we have to minimize losses. The waveguides we can produce can have losses as low as 0.03 dB per centimeter. This is directly measured. They could be even lower, but this is really important where you have to focus on quantum application that you have extremely low loss waveguides, because this is quantum decoherence which you can't compensate. And the second step, we do periodic domain inversion. And this is again done by photolithography and then high voltage applications such that we have domain probes and we can do periodic polling. Well, this is needed for quasi-phase matching. This gives us the flexibility of our devices. We can have type 2 and type 1 processes, for example, parametric down conversion processes, where we had been focusing over the last year to really get these polling periods smaller and smaller. So why is that? Why is that interesting for quantum applications? Well, let me show you first one of the things where we produce a rather good sample. This is a lithium niobate waveguide with a polling period of 1.7 micrometers. Here you see the photograph and the cross sections. And this was motivated by a quantum application because we wanted to produce counter-propagating photon pairs. So what that is, we pump this waveguide with our pump pulse, but the idler with a signal pulse propagates, well, in the normal direction like the pump, but the idler pulse propagates in the opposite direction. For that, you need these extreme gratings. Now, this is interesting because you can separate signal and idler quite nicely, but it has a different big advantage. And for that, I would like to look at this joint spectral amplitude. We will see more later on, where this is the frequency of the signal, this is the frequency of the idler. And here you see now the spectral properties of signal and idler. And what you can immediately recognize that the signal is in the terahertz regime bandwidth, where the idler has gigahertz bandwidth. So you can bridge bandwidths and you can convert bandwidths. And this is a highly attractive feature, which you can, for example, think of being useful for bridging stationary to flying qubits. And this is one of the applications where you see you need really advanced technology if you want to do specific quantum applications. Now, I told you that we can produce rather large, long waveguides. This is true. However, in theory, we always assume that we have very homogeneous systems, and also for the periodic polling, you really need, if you rely on the phase matching, homogeneity. Now, for the experts, and this is known in the classical photonics for quite some while, what's happening is that you never can avoid fabrication errors. What that does, it destroys your phase matching, so to speak, and this destroys that you only have an effective length, so you have to have very uniform systems. If you don't, you have fabrication errors, and the fabrication errors limits the usefulness of length of waveguides in these nonlinear crystals. And we studied the impact on quantum optics applications. So here you see this delta omega is basically a way of quantifying how much error you have and the maximum conversion efficiency over different lengths. And what you find, if you translate that into quantum applications, that this minimizes or this keeps the bounds of how much squeezing you can produce in direct paths, or also if you want to establish high-dimensional information encoding, for example, encoding the frequency domain, also this imperfection can impact that. Now, if you're interested, you can read that, but what I want to show you with these transparencies is basically that we really have to start to work from the technology and understand what that does for our quantum applications. Now, you might think, okay, you analyzed your own system. This is a lithium niobate waveguide. This is very specific. In fact, this is much more general. We found that if you look on different nonlinear interactions, different pair production schemes, on different materials. This is lithium niobate, KTP, also LNOI or photonic crystal fiber, that you always have a very similar scaling rule. And with that, you can come up with design rules. We say, okay, if I want to have that and that error, and I want to have this in fidelity, I have to do the specific things. Again, if you're interested, I'm happy to talk more about, but we also wrote that up to give you some guidelines how to design such systems. Now, this is a toolbox of our quantum circuitries altogether. Let me try to look into that again. I talked about the generation of photon pair generation. You can have up and down conversion. You can have memories. We have the passive ruling as a toolbox. We have the active manipulation, which is also important. And last but not least, we also have to think about interfacing, because we produce these waveguides, we manipulate our light in these waveguides, but then we quite frequently want to bring it somewhere else, for example, connecting to fiber and connecting to a fiber network. Now, the way you do that is either by fiber pigtailing or dielectric coatings, so we also have to care about that. I'd like to emphasize that many of these components, or most of them, have been developed for optical application, telecom and sensing, but now you have to tailor them for quantum applications. You have to optimize different parameters. And first for the interfacing, so all our waveguides have coatings, dielectric coatings, and this is, for example, the coating of the output of such a parametric down conversion source, where you see that the pump wavelength is suppressed, while this source produced 800 and 1600 nanometer photon pairs, where you see that we have huge AR coating. And then you do the pigtailing, where you also optimize their efficiencies. Up to now, we have routinely efficiencies above 85%. This is good on the one hand from the technology side. From the quantum side, we want to have it much better. So really having a better coupling to the fibers is also an important thing we are working at. And this is really for establishing the technology. This kind of work has to be done. Now, let me give you a brief overview about these different devices we have been doing. And I was curious to see, okay, what kind of devices can we implement where we know they exist, where they use this parametric down conversion in bulk systems, but we want to miniaturize it and make really, well, things which you can carry away and toy away. So we have implemented a plug-and-play single photon source, which is highly stable and has higher Ralding efficiencies. We have implemented a source for noon state, a very efficient one, which is basically a periodic pole direction coupler. We have implemented something what a generator of polarization entanglement of degenerate photon pairs. I like to call that a clear type source, where you basically just generate polarization entangled pairs, which is degenerate in frequencies but at different spatial things. We have looked at cascaded processes such that we generate free photons, but I can't go into detail of all of that. I'm happy to show you one. But what I wanted to show you here is our latest chip, which is a homomandel interference chip. And this is because it's a good benchmark chip and show you what we can do. So what is it? This is a monolithic integration of a parametric down conversion source and a 2-photon interferometer with a delay line. And you see that a lot of different components have to come together. So we start off with a PDC source of type 2, generating photons into different polarizations. Then we have a polarization converter here, and this is a segmented polarization converter in a 50-50 beam splitter. And the purpose is to generate 2 photons and let them interfere in a homomandel interference way to show anti-bunching. So let me go through the system that you understand what's happening. So we pump our system. One pump photon is decaying in a signal idler photon of 2 different polarizations. We switch the polarizations. You will see them into YB2 of that. And then we have a polarizing beam splitter, which separates horizontal and vertical photons. And here, this is again a polarization converter, but it's segmented. And depending which segment we switch on, at this point, we find that it's the polarization is changed, and the 50-50 beam splitter. And if you do that with the correct segment, you see the photon bunching, that both photons end up in one detector, but never any coincidences, like you know from homomandel interferences. Now, the point is, because our material is birefringent, if we switch at a different point, this photon on the top has traveled different, with a different polarizations, which means different lengths, and thus we can introduce a variable delay, which we can switch by electro-optics. And this is a situation, for example, these 2 photons don't see each other, you don't get the bunching effect, but get coincidences back. This is a theory depending on which segment you switch. This is a coincidence probability. Well, if you switch the correct segment, you don't get any coincidences, while if you switch them such that you get the classical situation back, so to speak, no quantum interference, you see that you get 50% coincidences. And now you also understand why we switched from the beginning. If you don't do something at the beginning, we always have a delay, and we see that as a calibration. This theory, this experiment, we see that's almost the same. And basically what we could prove with this system is that we had a homomundal interference of a visibility of 93% and a time delay of 12 picoseconds. And this you can think as a synchronization tool in quantum communication systems, but for us it's also showing a benchmark device that we kind of can handle the technology to that point. Okay, with that I would like to switch gears. And I promised you that I want to show you on the one hand the technology and the devices, and I did that. Now let me start again and start from a completely different perspective, from the fundamental quantum optics perspective. And in this, I want to talk about temporal modes of pulsed light. So let me start to explain you what that is about from the beginning. So I first want to introduce temporal modes of pulsed photons. So what is that? Well, if you go to your standard quantum optics lecture, you will learn a lot. And the first thing is that you learn, well, we have kind of an harmonic oscillator, and we quantize this harmonic oscillator. Well, we have a harmonic oscillator, mean that you have a monochromatic wave which you quantize. Now, if you're thinking of that in a, well, experimental scenario for quantum communication, you immediately find if you have a monochromatic wave and you Fourier transform that this monochromatic wave corresponds to a system where we basically have, well, a state with infinite timing. And you could immediately see this is 0 bit rate. So this is not a realistic scenario. If you want to have a single photon which can be used for anything, you have to come to a situation where we have something which is limited in time, but in order to achieve that, you have to have also a spectral spread of these things. Basically, you need a wave packet. And this is where we introduce the temporal mode operator called capital A, which is basically the superposition of different frequencies. If you Fourier transform that, then you get a nice Gaussian wave packet, and you really have a nice system. But now the quantization is done over these superpositions of different frequencies. Now, if you have that, you have on the one hand the temporal envelope shape, which is denoted by by some function fj. But of course, and then you have your field underlying that. What you can do now is you are allowed to define all kinds of different envelope functions. And in particular, you can define envelope functions which are field orthogonal. And if you do that, you have defined a Hilbert space, and you can define that. You have defined different entities of these temporal modes, which for all kinds of practical purposes, you can think of them as if they were monochromatic waves. So they are completely independent, and you have formed a new mode basis. Why would you want to do that? In particular, because these temporal modes, one note I want to make, they overlap in frequency and time. So this is a little bit of a weird structure, and we have to come back to that later on. And I have to explain to you how we can kind of deal with that. Now, why do we want to do that? And for that, let me go back to the history. As far as I know, in our context, it was not that we introduced them first and then we were looking where can we use them, but it's quite the opposite. They naturally arise if you analyze what a parametric down conversion, the same we just had with energy and momentum conservation, will do. So if we look for that photon pair generation. And let me sketch in a nutshell what I mean by that. So again, we have a nonlinear waveguide, very much the same we had it before. And we pump it again by a classical pump pulse, where one photon, here pump photon, decays in signal and idler photon, here shown in red and green. Well, we want a pulsed system, so let's start with a pulsed pump pulse. What you end up with, yes, is for sure something where this signal idler photon pairs also have some pulse characteristics. And there you see where these temporal modes, where we also have this pulse come or again. The way we can characterize them is by the joint spectral amplitude. Again, this is the frequency of signal, this is the frequency of the idler, and f omega is I, is the frequency of this joint state. What you normally will find is that this will have a correlated function. This is basically resulting from energy momentum conservation. Well, and now you ask, how can I understand that? And then around 2000, Lorworms and Eberle, I think, were the first who said, well, let's use this mathematical tool of a Schmidt decomposition, and then we know what's happening. Well, this is rather complicated, and I will try to give you kind of a picture way what it means.
Christine, we have a real-time question from Paul Kwiat. I don't know if you can see it in the chat. If not, I can read it to you.
I don't see it in the chat at the moment.
Yeah, it's hard to find it, but I'll read it to you. How good of waveguide PBS can you make?
Oh, this is for the other thing. Oh, I think, well, I have to see for the PBS, but I'm pretty sure that it's 100 to 1 is feasible. And as you probably know, it depends. If you say how good is it, I have to define which port it is. So I can have better suppressions, but then it's less symmetric. Does that help?
Okay, thanks.
Okay.
Yep, he says thanks.
Okay. I don't know, maybe this is a good time to interrupt very briefly if you're already there, if there's more questions for the technology part.
I'll let you know if a question pops up. Otherwise, let's move along.
Okay, fantastic. Let me continue with the Schmidt decomposition. Okay, so we have the system that a pump pulse pumps these nonlinear waveguides, and then what's happening is the following. Yes, this photon pair decays with some probability in a signal-idler photon, but they have very specific properties in the temporal mode basis. What it means effectively, whenever I have a Gaussian wave packet in the red, let's call it signal, I also have the idler in the Gaussian wave packet. It can equally happen, or with some probability, that it decays in the first Hermite mode, but then the corresponding also is in the first Hermite mode, and you probably will immediately see that we create correlations between these temporal modes and this entanglement between these modes. And again, we can play with the Hilbert space. Now, for many applications, people didn't want to have that, and spectral source engineering by now has become a tool. What you wanted to have is not to have these different modes. So this is effectively Schmidt numbers denoting you the probability that in these different modes you occur. And what you want to have is you only want to have Gaussian wave packets generated. And you do that by controlling the spectral correlations. And then you have the situation that you really can nicely produce photon pairs only. This is a scenario we also did that in 2011 with a waveguide. And why would you want to do that? Well, it's obvious because you do that. This is kind of an ideal source for integrated networks with multiple spatial channels. It's a pulse light source. You can do synchronization of condition and preparation. You can have high purity states, and you can also have extremely high brightness. So this is kind of a route which has become an established tool for people working with chromatic down conversion. However, what I want to present you now is that you can also go the opposite. Let's think that we are starting with a source engineered system where we have this decorrelated state. We have another degree of freedom we can play with. And this is, now let's shape the pump. We haven't been talking, up to now we always had the system pumped by a Gaussian pulse. But we can also start shaping the pump pulse. What you can do with that is that you can now completely control the Hilbert spread of the signal and idler photons and create, on your will, high dimensional states in these temporal modes. And here on this example, you even can make it such that you directly can make sure that signal and idler photons are all basically have equal probabilities, and they come in these pairwise systems. Why is that nice? Well, you can use these modes for information encoding, for networking, for all kinds of things. And we show in our newest work that we can really control this degree of freedom. Now, this is all fine, but I want to come back what I said earlier. These temporal modes overlap in frequency and time. And here, the signal states which we just had are shown in red again. Well, if they overlap in frequency and time, so you might ask, how can I separate them? Because if I can't access them, I can't do encoding, this doesn't help. And the way you can address these different temporal modes is by a tool which we invented, which is the quantum pulse gate. What that does, or what it is basically dispersion engineered sum frequency generation, which is single mode for that sum frequency. And here for the expert is a transfer function, which is flat. I don't want to go into detail here, but on these pictures, I can explain to you what happens. So for that sum frequency, it drives it again with a second pump, and this can have some specific shape. Depending on which shape, so this pump is a knob for me, I can decide which of my modes I'm addressing. So in the first case, I'm addressing the Gaussian. Everything is transmitted except this Gaussian part is converted to different frequency. If I dial up a different shape, I can convert a different temporal modes over, and so I can separate all that out, I can analyze them, and I can play with them. Now, we looked into that, and if you're interested in that, based on this principle, you can now come up with a complete framework for quantum information science, and we did only 5 years ago a theory together with Mike Raymer, where we showed you different applications you can have once you can control these systems. And if you want to know more about the space engineering and how you do that, we also have a quite detailed technical report, how you really can tailor the nonlinear processes. Now, for implementing, this is also one of the first pulse kits we had. And now it's coming back to the technology. If you ask, you need very specific dispersion properties, you need quite specific waveguides. The waveguides we're using is actually our lithium niobate waveguides. They have crystal length about 15 to 40 millimeter. It's a conversion process from the telecom, where the signal photons are, so where we have that, with a 800 nanometer, well, a pump around 880 nanometer, and it converts it to 575. That's quite convenient because we need pulse shaping, and this pulse shaping in the TISAF range is very efficiently possible. We need it, and this is why we started this small polling periods, rather small polling periods. We also need the titanium and diffuse waveguides. We need both modes. You can have temperature stabilization. Again, a side remark, you can also do bandwidth compression with this system. Now, this is then the first large experiment we did with that. We wanted to combine this PDC source, where I explained to you that we can control this Hilbert space, where we control the entanglement between these things, and where we know how to play with the joint spectral amplitude with our quantum pulse gates and do correlation measurements. By doing these correlation measurements, we can analyze now the states in the temporal mode. And this is now a temporal mode tomography. And if you ask me how this tomography does, it's really the standard tomography for a 7-dimensionally tomographically complete set. And here you see the different sets we did dial up, and we looked for all kinds of coincidences. And then this set we used for actually programming our quantum pulse gate. And then we produce parametric down conversion states with very specific spectra, the way I showed you before. First, we started with a decorrelate spectra, and this is a joint spectral intensity. And from this joint spectral intensity, you see that there should be no correlations. And because there is no correlations we're in the situation which I showed you as the ideal source, we should have only one temporal mode, theory and experiment, and it worked out quite nicely. Then we introduced some correlation, and what you expect is that more other modes appear, and you also could see that with that system we could prove that, and we could show that this works quite nicely. One thing to notice, however, be careful. This is just an intensity measurement, so we deliberately introduced a spectral phase, which you normally never see, and what you immediately see is that the system becomes highly multimode. And this is a warning, but also interesting. So we can also play with the phase, meaning the timing information. By the way, for the experts, you probably know that you can measure the purity, but also the G2 values, and we compared that, and that also worked quite nicely. We liked that a lot because that means that we can control that. And then I showed you that I can play with the pump, and I can switch to a system where I can have different temporal modes, and this is actually a Bell state entangled mode. And we also could show that with the quantum pulse gate that this works. And well, I'm happy to talk more about that. I think I have something like 5 to 10 minutes left. Is that correct?
Sure, you can go ahead and take whatever time you would like, because we don't have a poster presentation. So, you can go up to 20 minutes if you'd like.
Okay, so let me take the opportunity So this is great because this is, again, we just now in the lockdown, but we can play with the system. We have now the possibility in code information to have entanglement and really play with these temporal modes quite nicely. One thing I would like to mention at that point, these temporal modes are nice because you probably have heard about orbital and angular momentum modes where you can also encode and do the same things. It's actually our work inspired. But this should be not affected by dispersion, so it's highly compatible with all waveguide systems. Now, I would like to switch gears. This is why I asked for the time. Once we had this quantum pulse gate, we realized that this is not only useful for communication technology, but actually also has a very nice application for quantum metrology. And this is very similar and inspired by I think by now famous work of Zhang, where this relates to super resolution. So let me briefly introduce what that is about. So basically, this is a situation where you have in the spatial domain two different emitters, incoherent emitters, and you bring them closer and closer together and you ask, how long can I distinguish them? In our case, these emitters are not spatially separated, but by frequencies. But again, if you bring them closer and closer together, at some point you would expect that you can't distinguish them anymore. And the reason is basically that this is limited by Rayleigh's criterion, Rayleigh's cause. Now, what was realized here is that this is not true for the quantum situation. So the quantum limit and the Kramer-Rao bound, which is behind that, if you make that separation smaller and smaller and smaller, tells you that you can always distinguish that if you do the correct measurements. What are these correct measurements? Well, the correct measurements is actually that you're measuring in superpositions, of space, or in our case, in superpositions of these different frequencies. But this is exactly what the quantum pulse gate can do. We can measure coherently over these different frequencies. And this is where, again, a setup for these quantum pulse gate setup where we have now the SLMs explicitly, we have a signal pulse shaper where this basically defines for us these two different signal pulses which we want to distinguish, which we bring closer and closer together. And incoherence we can model by putting different measurement sets together. And then we have this projector, which is basically the pump of a quantum pulse gate where we can separate these two things. And what we have to measure is again in these Hamid modes. If you do everything correctly, what you can do then is that you can prove this super resolution. And we started that with single parameter estimation with a balanced source. So what I mean here, you can find all the quantities here on the left-hand side. So the quest is you have two emitters which are incoherent, have two different frequencies, and we bring these frequencies closer and closer together and ask, can we still distinguish them? Here you see that the separation gets closer and closer together all the way up to 0. This would be the classical bound, the blue one, but you can see that we can nicely demonstrate that we can measure that quite nicely. We can still distinguish that. Again, here you have the parameter separation and the estimated separation. You expect a linear behavior. You see these different scenarios while you're running here in some experimental imperfection. But it's really, for us, it was fascinating to see that because we could really estimate down to the femtosecond regime for these separations, and we really saw in the vibrations, or we had to be sure that everything is very stable, but we could measure that very nicely. Now this was great, but we can do more, and this goes to multi-parameter estimation because we only up to now looked into the situation where these two things have equal, while they're exactly equal. So we wanted to have a situation where we have to estimate more parameters, such that we don't know that we have equal intensity of those, and we also don't know where the centroid is. So basically, we allowed for unequal intensities, some separation S, and the centroid is 0. So these are the parameters which we have to estimate. And I should say we worked there together with collaborators, with Santi Soto and Yasmin Hajik. This is the definitions, and basically, this theory, how much you can estimate if there's multiple parameters which do not commute, is rather intricate. But what was nice for us is that we really could demonstrate also this in the lab again. So this is the experiment. we wanted to have the multi-parameter estimation, where here you see which different parameters we wanted to estimate, the distance, the centroid, which is different, or the different heights of these systems. And then we have here on this graph the quantum measurements with our quantum pulse gate. And on the other hand, we have the classical limits in this gray shaded region. And what you can see here is that effectively, yes, it does work. So we could demonstrate in the experiment that we could implement this parameter estimation. And we think this is quite nice because this works for time and frequency. And this means that this coherent detection, which we have implemented for the quantum pulse gate, can actually be used also to do this quantum measurement and quantum measurement based quantum metrology on that. And this opens for us a new route, which we're exploring at the moment. And we really find that this quantum pulse gate probably has much more applications than we thought at the beginning. With that, let me sum up. So I tried to give you a glimpse on what we're doing in the field of photonics for quantum applications. And in the first section, I showed you quite a lot of work, which is on the technical side of technology, and showed you which devices we can build up. And we are right now building up also different devices and look for more direct applications. And the second part of my talk, I showed you and introduced you the concept of temporal modes of pulse flight, where a lot of our work is really based on the one hand on engineering these temporal modes, and on the other hand, to be able to select these individual modes and kind of do a lot of the concepts which you used in space, you can translate them in the time temporal frequency degree of freedom. And I think both of these, well, we can explore now different things. And well, unfortunately, we had to stop some of the experiments so that I couldn't show you more. We're on the way to have more data there. But anyhow, I hope this gives you a glimpse of what we're doing in my group. And before finishing, I would like to thank you for the attention, but I really also would like to thank my group. It's not only my work, but there's a lot of people involved, a lot of people who are really, well, doing a great job. And this is, I want to thank my group, and of course also my sponsors. And with that, I'm at the end, and I'm happy to take some more questions from you.
Okay, thank you, Christine. I'm clapping on behalf of everyone out there who's muted, and we have plenty of time for questions. Also, what kind of candy do you have?
Everything you want. No, maybe, well, cake if you want.
Yeah.
I don't know. I have to see if I see it. So should I stop my presentation here, or how should I do it?
Either way, you should be able to see the chat box underneath the menu of possibilities. It might be under a more with the 3 dots.
I'm just looking for the chat. Let me stop the presentation for the moment that I see the chat. Okay, here I see the chat.
There you go. Another question there from Paul Kwiat.
Quick question on the integrated home grid. Is there any advantage to using several short segments instead of just varying the voltage of a longer segment? Oh, I didn't go into detail how these segments work. Actually, every single segment rotates the polarization. So you have to make sure that the segment completely rotates. So the length has to be very specific. So, and the time delay simply comes from a factor where I am. So I can't use just different voltages over different segments, but I have to do the segmented things because it's a polarization converter.
I had a quick question. You had a couple. Paul says it's not a phase delay. I understand. What I was going to ask is, you had a few plots showing loss versus a parameter, which I don't know if it was sigma W or delta W, but was that the RMS deviation from a plane?
Is that for that imperfections?
It was the waveguide, I thought. It was the imperfections in fabrication.
Yes, this is basically the error, the RMS, the white noise error.
Okay, so it's the RMS deviation from a plane.
Yeah.
And it looked like it was on the order of a tenth or a couple tenths of a micron.
Less than that, much less. So we really have something in the range of tens of nanometer, which we have to control. If you really, so this is the problem. The amplitude of the imperfection can be rather low. This is what we realized. Actually, it came the other way around. We wanted to produce very long samples for the quantum pulse gate because they're the phase matching, and we realized that we couldn't do it as well as we thought. And then we calculated to which perfection you have to have the waveguide, and then we realized it doesn't work. So it's really, the waveguides are micrometers, but I think it's tenths of nanometers of imperfection which you have to control. It's almost unmeasurable for us. So it's really very harsh.
And is the coherence highly sensitive to temperature? Do you have to control temperature?
You have to control temperature. A temperature per se shifts your whole phase matching. You can even use that. A temperature is not really problematic, but temperature gradients, you have to be careful.
Okay. You have a question from Chris Maloney there.
Do you have some modeling solutions in place for your nonlinear integrator to simulate full circuits? You mean with all imperfections? No, not yet. We don't have, we are starting we can model our waveguides and the nonlinear processes, but not complete circuitries yet. So this is like you have in normal integrated optics, we have these FAB tools, but we don't have that here yet. Hi, Christine. With multiple channel and temporal modes in PDC, the G2 is degraded. What's the reason? With multi-channels, well, the G2 is small, so this is a kind of, I guess you're referring to where I said you can measure the purity by measuring the G2. The idea behind that is that if you have a single mode system for this PDC, you can understand that as a two-mode squeezer. And if you trace out of a 1, this is what the G2 measurement is doing, you get a G2 of 2. This is simply because it's thermal statistics. Now, if you have multiple modes, you're convoluting a lot of different thermal statistics. And if you do that, you go back to Poissonian. So this is why the G2 gets smaller. So this is the way you measure this G2 value. So this G2 can serve you as a direct measurement of multimodeness. We have an NJP listed all if you're interested in that. It's used a lot these days.
Well, it looks like that's about it. And we're nearing the top of the hour. So Christine, I wanted to thank you once again and remind people that they can see the recording, which we'll post probably later this afternoon. Otherwise, as I said before, we're skipping tomorrow, and then we'll come back on Wednesday and Thursday, and that'll be the end of the workshop. So thanks, Christine, and be well. Good evening for you, and take care. We'll see you. Bye, everyone.
Bye-bye.
Bye, Christine.
Bye-bye. Bye-bye, Paul.
Bye. Great to see you.
Nice to see you too.